Obviously, our computers didn't start talking natural language overnight. A lot of research has been going into the field of artificial intelligence and natural language. Let's take a quick peek under the hood of what is happening in our second episode of Demystifying Generative AI. So what exactly happens when you're talking to ChatGPT? Well, your inputs get fed to a statistical model. You give it a certain prompt and the model will predict and output a response. This model is the artifact of a training. And as we've mentioned in episode 1, for a model to learn, it needs data. The machine learning paradigm applied will depend on what data is available. We can apply supervised learning when labeled data is available, unsupervised learning when no labeled data is available, or reinforcement learning, in which the model tries to take some actions and it gets penalized or rewarded for those actions. And at the end, the model tries to maximize its rewards. At the core of the latest generative AI wave sits language modeling, which is why you will hear a lot about large language models or LLMs, which learn in a supervised way. These models are trained on huge corpora of data, and more particularly text data. Datasets include data from websites like Wikipedia and fora like Reddit, as well as books and even code from a website like GitHub. During training, sentences get chopped up in little bits and the model will attempt to predict the next word. The artifact of this process is a pre-trained model, which can then be further fine-tuned to do specific tasks like question answering, or it can be trained on a domain-specific dataset to answer more specific questions about the domain you're interested in. From a research perspective, the foundation for LLMs was laid in the 2017 paper Attention is All You Need, authored by the researchers at Google Brain. And I think it's important to cover some of the concepts that were part of that paper. The paper introduced transformers, a neural network architecture that solved some of the problems faced earlier in the field, like the sequential processing from recurrent neural networks and the finite memory from convolutional neural networks. Transformers made parallelization and long-range dependencies within text possible. Especially parallelization was quite important, since now optimized hardware could be used for faster training and inference. This also caused a boom in the market for specialized chips, and especially GPUs, which you might have noticed if you're looking at Nvidia's stock price, which 10x over the last 4 years. Digging one level deeper, we find that the transformer consists of multiple encoder and decoder blocks. Each encoder block has a self-attention layer and a feed-forward layer. The self-attention layer is the most important part. You can think of it as a way for the model to measure the importance of different parts of the input sequence relative to each other. The output of the encoder layer becomes the input of the decoder component, which has a feed-forward layer, a masked self-attention layer, which prevents the model from attending to future information, and an encoder-decoder attention layer, which helps it focus on relevant parts of the input sequence. Since in language the position of a word is of importance, we can also inject some of this information with something what is called positional encodings. This architecture remains the backbone of newly released models, which continue to be researched and refined. Some of the popular models only use parts of this architecture though, like BERT, which is based on an encoder-only architecture, while the GPT family only relies on the decoder component. I hope this episode tickled your interest to go and read the paper. Let us know what you've learned below in the comments, and if there's any other content you would like us to cover.